Well, hope you're doing well today. Today we're continuing our conversation in chapter 9. This is part 3. We're working on regulation of body temperature. Here we go. Normal body temperature can vary slightly depending on the method of measurement and the individual. However, the generally accepted normal body temperature ranges are as follows. For oral or mouth temperature, the normal range is usually considered to be between 27.6 degrees Fahrenheit and 99.6 degrees Fahrenheit. The average oral temperature is typically around 98.6. Rectal temperature, the normal range for rectal temperature is slightly higher than oral temperature. It is usually between 98.6 and 106 degrees Fahrenheit. Esophageal temperature is measured by placing a probe into the esophagus. The normal range is similar to rectal temperature, typically falling between 98.6 and 100.6 degrees Fahrenheit. And the temperature inside the GI tract can vary depending on the location. The core body temperature is generally considered to be around 98.6 degrees Fahrenheit and can change slightly along the GI tract, depending on factors like food intake, digestion, and environmental conditions. It's essential to remember that body temperature can fluctuate throughout the day due to various factors such as physical activity, emotional state, and hormone levels. Additionally, individual variations can occur and certain conditions or medications may influence body temperature as well. The shell temperature, also known as skin temperature, refers to the temperature of the outer surface of the body, specifically the skin. It is different from the core body temperature, which represents the temperature of the body's internal organs and tissues. Shell temperature can vary considerably based on environmental factors, physical activity, clothing, and individual differences. The normal range for skin or shell temperature is typically lower than core body temperature and can be affected by various factors. The ambient temperature, which is the surrounding environment. If it's cold, the shell temperature tends to decrease, and vice versa for warm environments, like where we are in Corpus Christi. Clothing, the type and amount of clothing worn can insulate the body, affecting shell temperature. Physical activity. So engaging in physical activities can increase shell temperature due to increased blood flow to the skin. Poor circulation can result in cooler skin temperatures. And during a fever, the body's core temperature increases, leading to an elevated shell temperature as well. It's important to note that measuring shell temperature is not a precise method for assessing overall body temperature. For accurate body temperature assessment, core temperature measurements such as oral, rectal, or ear temperature are more reliable. Several major factors influence body temperature, and they can be summarized using the heat balance equation, which takes into account various mechanisms of heat gain and heat loss. The heat balance equation is as follows. H equals RMR plus or minus W plus or minus cond for conditioning or conduction plus conv for convection and plus or minus radiation minus evaporation. So where H represents heat production or heat gain by the body, RMR stands for resting metabolic rate, which is the heat produced by the body at rest. W represents the work done by the body, such as exercise, which generates additional heat. And cond represents heat gained or lost through conduction, which is the transfer of heat between objects in direct contact, such as sitting on a cold surface. Conv, on the other hand, represents heat gained or lost through convection, which is the transfer of heat between the body and the surrounding air or fluid, such as air currents or water immersion. R represents heat gained or lost through radiation, which is the transfer of heat in the form of electromagnetic waves from the sun or body's infrared radiation. And E represents heat loss through evaporative heat loss from sweating, which is a cooling mechanism when sweat evaporates from the skin's surface. These factors work together to maintain the body's core temperature within a relatively narrow range to ensure proper physiological functioning. For example, in a cold environment, the body may increase heat production, RMR and W, reduce heat loss through conduction and convection, and minimize sweating to conserve heat. In a hot environment, the body may decrease heat production, increase heat loss through conduction, convection, and radiation, and promote sweating to cool down. And during physical activity, the body generates additional heat, and to prevent overheating, it increases heat loss through evaporation and other mechanisms. During a fever or infection, the body's heat production increases as a part of the immune response, and fever-reducing mechanisms may be activated to restore the balance. These processes collectively contribute to thermoregulation, which helps maintain a stable body temperature and enables the body to adapt to various environmental conditions and metabolic demands. Exercise, the body undergoes increased metabolic activity, which generates additional heat. To prevent overheating and maintaining a stable core body temperature, the body relies on several heat exchange mechanisms to dissipate the excess heat. The major heat exchange mechanisms during exercise include evaporation. As physical activity increases, the body's temperature rises, leading to the activation of the sweat glands. Sweat is produced and released onto the skin's surface. As the sweat evaporates, it absorbs heat from the skin, effectively cooling the body. Evaporative heat loss is one of the most important cooling mechanisms during exercise, especially in hot and humid conditions. During exercise, air movement around the body, or convection, plays a role in heat exchange. As the body generates heat, the surrounding air heats up, and if there is airflow, the warmer air is replaced by cooler air. This helps in dissipating some of the excess heat from the body. The body continuously emits radiant heat in the form of infrared radiation. During exercise, as the body's temperature rises, the rate of heated radiation also increases. If the surrounding air temperature is cooler than the body loses heat through radiation. Conduction is less significant during exercise because it involves direct contact with surfaces of different temperatures. However, when the body touches cooler surfaces, again, such as sitting on a cold bench, some heat may be transferred to that surface, contributing to heat loss. It's essential to note that the effectiveness of these heat exchange mechanisms depends on environmental conditions such as temperature, humidity, and airflow, as well as individual factors like fitness level, clothing, and hydration status. In hot and humid conditions, the body may face challenges in dissipating heat effectively, which can lead to heat-related illnesses if proper precautions are not taken. During exercise, maintaining adequate hydration is crucial as it supports sweating and efficient evaporative heat loss. Additionally, wearing appropriate clothing that allows moisture wicking and airflow can enhance the cooling process. Understanding and managing heat exchange mechanisms during exercise can help athletes and individuals engage in physical activity safely and efficiently. Temperature regulation is primarily controlled by a region in the brain called the hypothalamus. The hypothalamus acts as the body's thermostat, constantly monitoring the temperature of the blood and making adjustments to maintain a stable core body temperature. It receives input from various sensors throughout the body and responds to changes in the environment, ensuring that the body's internal temperature stays within a narrow range for optimal physiological function. The key components involved in body temperature regulation and the hypothalamus control include thermoreceptors. These are temperature-sensitive nerve cells located throughout the body, primarily in the skin and internal organs. They constantly send signals to the hypothalamus about the temperature of the blood and surrounding tissues. The hypothalamic thermoregulatory center is where it contains two main areas related to temperature regulation, the heat promoting center and the heat dissipating center. These areas receive input from thermoreceptors and integrate the information to determine the appropriate response. When the hypothalamus detects a drop in core body temperature, it triggers various physiological responses to increase heat production and conserve heat. This may include vasoconstriction or narrowing of blood vessels, shivering, which is rapid muscle contractions, and the release of hormones like norepinephrine. The heat dissipating center senses an increase in core body temperature, and it initiates a converse mechanism to promote heat loss and cool down the body. This includes vasodilation or widening of blood vessels, sweating, which is evaporative heat loss, and behavioral responses like seeking shade or removing layers of clothing. The hypothalamus has a set point for body temperature, which is the desired temperature range for optimal physiological function. When the core body temperature deviates from this set point, the hypothalamus activates appropriate responses to bring it back to the normal range. The hypothalamus continues receiving feedback from thermoreceptors and other sensors to assess the effectiveness of its temperature regulation efforts. If the body is not reaching this set point, the hypothalamus adjusts its responses accordingly. Overall, the hypothalamus plays a crucial role in maintaining homeostasis by regulating body temperature. It ensures that the body can adapt to changes in the environment and metabolic demands, allowing for optimal functioning of various physiological processes. When the hypothalamus temperature regulation is disrupted, it can lead to conditions like hypothermia, which is an abnormally low body pressure temperature, or hyperthermia, which is an abnormally high body temperature, which requires prompt medical attention. So the thermoreceptors that are located throughout the body are sensors that detect changes in internal and external temperatures. The hypothalamus is the brain's thermostat. The hypothalamus receives input from the thermoreceptors. Now, the hypothalamus maintains as a target a set point for the body's core temperature, usually around 98.6 degrees Fahrenheit. And the hypothalamus continues comparing the current body temperature to set points. Now, if the body's temperature falls below the set point, then heat promoting mechanisms are activated. There's vasoconstriction that occurs. So blood vessels narrow, reducing heat loss through the skin. And shivering, so muscles contract rapidly, generating heat. There's also hormonal adjustments. Certain hormones like norepinephrine increase metabolic activity to produce more heat. If the body's temperature rises above the set point, then heat dissipating mechanisms are activated. So there's vasodilation, where blood vessels widen, allowing more heat to escape through the skin. Sweating, so the body releases sweat, which again evaporates and cools the skin. And then behavioral responses, seeking shade, removing layers of clothing, and drinking cold fluids. And the feedback loop. The hypothalamus receives continuous feedback from thermoreceptors to adjust its responses as needed. Now, in temperature regulation, the hypothalamus works to balance heat gain and heat loss, aiming to maintain the body's core temperature within the desired range. This simplified schematic illustrates the dynamic interplay between the hypothalamus, thermoreceptors, and various physiological mechanisms that work together to regulate body temperature and maintain homeostasis. Hypothermia and hyperthermia are both conditions related to the body's core temperature, but they represent opposite ends of the temperature spectrum. Hypothermia occurs when the body loses heat faster than it can produce it, resulting in a dangerously low core body temperature. The condition is typically defined as having a core body temperature below 95 degrees Fahrenheit. Hypothermia can be caused by exposure to cold weather, immersion in cold water, or prolonged exposure to low temperatures without adequate protection. Symptoms of hypothermia include shivering, confusion, drowsiness, slurred speech, weak pulse, and loss of consciousness. Severe hypothermia can be life-threatening and requires immediate medical attention. Hyperthermia, on the other hand, occurs when the body's heat production exceeds its ability to dissipate heat, leading to an abnormally high core body temperature. Hyperthermia can be caused by exposure to high environmental temperatures, strenuous physical activity in hot conditions, or a malfunction in the body's temperature regulation mechanisms. Heat exhaustion and heat stroke are examples of hyperthermia. Symptoms of heat exhaustion include heavy sweating, weakness, dizziness, nausea, and headache. Heat stroke is a medical emergency and is characterized by a core body temperature above 104 degrees Fahrenheit. Confusion, rapid heart rate, dry skin, and loss of consciousness. Heat stroke can be life-threatening and requires immediate medical attention. In both cases, it is essential to take preventive measures to avoid these temperature extremes. In cold conditions, dressing warmly, staying dry, and seeking shelter are crucial. In hot conditions, like we're having right now, staying hydrated, wearing lightweight and breathable clothing, and avoiding excessive physical activity during peak heat hours can help prevent hyperthermia. Air temperature, relative humidity, air movement, and radiation are all key environmental factors that influence the body's heat exchange and consequently play a significant role in thermoregulation. Here's how each factor affects the body. The ambient air temperature is a crucial determinant of how the body loses or gains heat. In hot conditions, the air temperature is often higher than the body's temperature, which can hinder heat dissipation, leading to an increased risk of hyperthermia. In cold conditions, the body may lose heat to the environment, increasing the risk of hypothermia. Relative humidity refers to the amount of moisture in the air relative to its capacity to hold moisture at a given temperature. High humidity reduces the rate of evaporative heat loss through sweating. When the air is saturated with moisture, like 100% relative humidity, sweat evaporates slowly, limiting the body's ability to cool down, which is a condition that we have here in Corpus Christi. Not necessarily 100% humidity, but it is fairly high. This can be particularly problematic in hot and humid conditions as the body struggles to dissipate heat effectively, increasing the risk of heat-related illnesses. Air movement, also known as wind speed or wind velocity, enhances the body's heat loss through convection. When there is a breeze or wind, it helps carry away the heat from the skin, promoting cooling. In contrast, still air impedes heat dissipation, making it harder for the body to cool down. Now, radiation involves the transfer of heat in the form of infrared waves between the body and its surroundings. So in hot conditions, the body can absorb radiant heat from the sun or other hot objects, adding to the heat load. On the other hand, in cold conditions, the body can lose heat through radiation to cooler objects or the night sky. The combination of these factors determines the net heat gain or loss experienced by the body during various environmental conditions. In hot and humid environments with high air temperature, high humidity, and limited air movement, the body's ability to dissipate heat through sweating and evaporation is compromised, increasing the risk of heat stress and heat-related illnesses. In cold conditions with low air temperature and wind, the body may lose heat to the environment, increasing the risk of hypothermia. For athletes and individuals engaged in outdoor activities, it's essential to be mindful of these environmental factors and take precautions to maintain proper thermoregulation. Staying hydrated, wearing appropriate clothing, seeking shade or shelter, and adjusting activity level based on the conditions can help mitigate the risks associated with extreme temperatures. Exercising in the heat can be challenging and poses increased risks of heat-related illnesses for athletes and individuals engaged in physical activity. To better understand the heat stress experienced during exercise in hot conditions, two important heat indices are often used: the wet bulb globe temperature, or WBGT, and the heat index. Both indices take into account various environmental factors to provide a more accurate representation of heat stress an individual may experience. Here's a brief explanation of each. The wet bulb globe temperature, or WBGT, is a composite index that considers air temperature, relative humidity, and radiant heat from the sun or solar radiation and the ground. It is commonly used in occupational and athletic settings to assess heat stress levels and guide decisions about exercising or working in hot environments. The WBGT takes into account the cooling effect of evaporative heat loss, or sweating, and the added heat from the sun and ground. It is calculated using the formula WGBT equals 7/10 times the wet bulb temperature plus 2/10 times air temperature plus 1/10 times the black globe temperature. The wet bulb temperature is measured using a wet bulb thermometer, which is a thermometer with a wet cloth covering the bulb. The air temperature is the standard temperature reading, and the black globe temperature is obtained using a globe thermometer that absorbs solar radiation. The heat index, also known as the apparent temperature, is a measure of how it feels to the human body when both air temperature and relative humidity are considered. It is used to assess the perceived temperature and the potential risk of heat-related illnesses. The heat index is calculated based on air temperature and relative humidity and provides an indication of how effectively the body can cool itself through sweating and evaporation. Higher humidity levels reduce the body's ability to cool down through sweating, making it feel hotter than the actual air temperature. The heat index is typically displayed in weather reports and is calculated using empirical formulas provided by meteorological agencies. Both the WBGT and the heat index are valuable tools for athletes, coaches, and event organizers to gauge the potential heat stress during exercise or outdoor activities. They help in determining appropriate precautions, such as modifying activity levels, providing ample hydration and rest breaks, and ensuring access to shade and cooling areas to minimize the risk of heat-related illnesses like heat exhaustion and heat stroke. It's essential to take these heat indexes seriously, as heat-related illnesses can be dangerous and life-threatening. Proper preparation and awareness of the heat stress levels can help athletes and individuals enjoy physical activity safely in hot conditions. The heat index is a measure of how hot it feels to the human body when both air temperature and relative humidity are considered. It provides an indication of apparent temperature and the potential risk of heat-related illnesses. As the heat index rises, the risk of heat-related illnesses increases as well. The main heat-related illnesses include heat cramps, which are painful muscle spasms that occur during or after intense exercises in hot conditions. They are typically caused by an imbalance of electrolytes due to excessive sweating. Heat exhaustion is a more severe heat-related illness that results from prolonged exposure to high temperature and inadequate fluid intake. Symptoms include heavy sweating, weakness, dizziness, nausea, headache, and rapid heartbeat. Heat syncope, or heat fainting, occurs when an individual stands for extended periods in hot conditions. It is characterized by lightheadedness and fainting due to decreased blood flow to the brain. A heat rash, also known as prickly heat, is a skin condition caused by blocked sweat ducts. It appears as small, itchy red bumps on the skin and is common in hot, humid conditions. Heat edema is swelling in the hands, ankles, and feet that can occur in hot weather, particularly in individuals who are not acclimated to the heat. And heat stroke, which is the most severe and life-threatening related illness. It occurs when the body's temperature regulation system fails and the core body temperature rises dangerously high levels, usually above 104 degrees Fahrenheit. Heat stroke is a medical emergency and requires immediate treatment. Symptoms include confusion, rapid heart rate, dry skin, and loss of consciousness. Again, it's crucial to be aware of the heat index and take appropriate precautions to prevent heat-related illnesses. Prompt recognition and treatment of any heat-related symptoms are essential for maintaining health and safety during hot weather conditions. Exercise affects body temperature by increasing metabolic activity, which in turn affects the body's specific heat capacity. Specific heat is the amount of heat energy required to raise the temperature of a unit mass of substance by 1 degree Celsius or 1 Kelvin. In the context of the human body, specific heat refers to the amount of heat energy needed to raise the body's temperature by 1 degree Celsius. During exercise, the body's metabolic rate increases to supply the necessary energy for muscle contractions and other physiological processes. As a result, more heat is produced by a byproduct of these metabolic reactions. The body's specific heat capacity remains relatively constant during exercise, meaning the amount of heat required to raise the body's temperature by 1 degree Celsius does not significantly change. Specific heat of the body is 0.83. 0.83 calories will raise 1 kilogram of body mass 1 degree Celsius. However, the increase in heat production during exercise can lead to an increase in body temperature. The body's thermoregulatory system, particularly the hypothalamus, responds to this rise in temperature by initiating mechanisms to cool down the body. The mechanisms include increasing blood flow to the skin, triggering sweating, and redistributing heat throughout the body. The normal body temperature at rest for a healthy adult typically ranges again between 97.8 and 99 degrees Fahrenheit. However, individual variations can occur and body temperature may fluctuate slightly throughout the day. The average body temperature often considered to be around 98.6 degrees Fahrenheit, but it's not an absolute value for everyone. It's essential to consider body temperature can be influenced by various factors such as age, gender, time of day, and activity level. In the early morning, body temperatures tend to be lower and it gradually rises throughout the day, peaking in the late afternoon or early evening. Body temperature can also be affected by factors like illness, hormonal changes, ambient temperature, and stress. For instance, during infections or fevers, the body's immune response can lead to an elevation in body temperature, and hormonal changes can cause variations in body temperature during the menstrual cycle in females. An increase in core temperature at rest with no heat loss. This is when you're resting for 60 minutes and you expend 80 calories. 80% of those calories are released as heat, or 64 calories. So if you have a 70 kilogram runner who's about 154 pounds, then a storage of 58 calories would increase body temperature by 1 degree Celsius. Again, specific heat is equal to 0.83 calories per kilogram of body mass. So 0.83 times 70 kilograms equals 58 calories. Body temperature would increase by 1.1 degrees Celsius if body heat is not dissipated. So 64 calories divided by 58 calories equals 1.1 degrees Celsius. And normal body temperature is typically, again, 98.6 degrees Fahrenheit. If no heat is lost, body temperature increases to 100.6 degrees Fahrenheit. What fun, right? During exercise, the body temperature increases due to the increased metabolic activity and heat production associated with physical activity. The rise in body temperature is a natural response to the increased energy demands of the muscles and other physiological processes involved in exercise. The extent to which body temperature increases during exercise depends on several factors, including the intensity and duration of the exercise, the environmental conditions that we've talked about, and individual factors such as fitness level, hydration status, and acclimation to the heat. As the body temperature rises during exercise, the body's thermoregulatory system, particularly the hypothalamus, responds to prevent overheating. That activates cooling mechanisms to maintain the body's core temperature within a safe range. So an increase in core temperature with exercise and no heat loss. So for someone who is running for 60 minutes can expend 900 calories. 80% of calories are released as heat, or 720 calories. The specific heat of the body is, again, 0.83 calories per kilogram of body mass. So if we have our 70 kilogram runner of 154 pounds, 0.83 calories raise 1 kilogram of body mass 1 degree Celsius. Storage of 58 calories would raise the body temperature by 1 degree Celsius. And body temperature would increase by 12.4 degrees Celsius if the body heat is not dissipated. So you have 720 calories divided by 58 calories equals 12.4 degrees Celsius. Normal body temperature, we all know now, is 98.6. If no heat is lost, body temperature increases to 120 degrees Fahrenheit. In a warm or hot environment, exercise can significantly increase the body's heat production, leading to an increased reliance on evaporative heat loss through sweating to dissipate heat and maintain stable core temperature. Evaporation of sweat is indeed a key factor in cooling the body during exercise in hot conditions. The percentage of total heat loss through evaporative cooling varies based on the ambient temperature. As the ambient temperature increases, the body's reliance on evaporative cooling becomes more critical. Here are the approximate percentages of total heat loss through evaporation at different ambient temperatures. At 50 degrees Fahrenheit, evaporation accounts for approximately 20% of total heat loss. In colder environments, the body relies less on sweating for cooling, since there is smaller temperature difference between the body and the environment. Other heat loss mechanisms, such as conduction and radiation, play a more significant role in maintaining body temperature. At 68 degrees Fahrenheit, evaporation accounts for approximately 45% of total heat loss. As the ambient temperature increases, the body's reliance on evaporative cooling becomes more prominent. And at 86 degrees Fahrenheit, evaporation accounts for approximately 70% of total heat loss. In hotter environments, the body heavily depends on sweating and evaporation to cool down. Conduction and radiation become less effective as the ambient temperature approaches or surpasses body temperature. These percentages illustrate how the body's cooling mechanisms adapt to different environmental conditions. In cooler temperatures, the body can rely more on other heat loss mechanisms. But as the ambient temperature increases, sweating and evaporation become critical for preventing overheating. It's important to recognize individual factors, again, fitness level, hydration level, and acclimation to the heat can influence the body's ability to regulate temperature and the effectiveness of heat loss mechanisms during exercise in warm or hot environments. Compensated heat stress and uncompensated heat stress are terms used to describe the body's response to heat exposure and its ability to regulate core body temperature. Compensated heat stress occurs when the body is exposed to heat, and it responds effectively by activating various cooling mechanisms to maintain a relatively stable core body temperature. When the body is in a state of compensated heat stress, it can dissipate heat efficiently through mechanisms like sweating, increased blood flow to the skin, and heat radiation. As a result, the body's core temperature remains within a safe range, and the individual does not experience significant discomfort or symptoms of heat-related illnesses. Uncompensated heat stress occurs when the body is exposed to excessive heat and its cooling mechanisms become overwhelmed or less effective in dissipating the heat. The body's core temperature starts to rise beyond the normal range, and the individual may experience discomfort, fatigue, weakness, and other symptoms of heat-related illnesses, such as heat stroke or heat exhaustion. In this state, the body struggles to regulate temperature, and the person may require immediate intervention to cool down and prevent heat-related complications. The ability to compensate for heat stress can vary among individuals based on factors, again, fitness level, acclimation to the heat, hydration status, and overall health. Additionally, environmental factors like high ambient temperature, humidity, and lack of airflow can influence the body's ability to cope with heat stress. It's essential to be aware of the signs of heat-related illness and take appropriate precautions to avoid uncompensated heat stress. Engaging in physical activity in hot environments requires staying hydrated, taking frequent breaks, seeking shade or cooler areas when necessary, and modifying activity levels as needed. Recognizing the difference between compensated and uncompensated heat stress can help individuals make informed decisions to protect their health and well-being during exposure to high temperatures. Heat can significantly impact physical performance during distance running and marathon running. Running in hot and humid conditions poses unique challenges to the body, affecting performance, endurance, and overall well-being. Distance running performance impaired, so significant linear relationship between WBGT and decreased performance in a 10-kilometer run. With marathon running performance, they have seen that running times decrease about 1 minute for every 1 degree Celsius that it increases beyond 8 to 15 degrees Celsius. Or if you want to put it in Fahrenheit, it's each 1.8 degrees Fahrenheit beyond 46 to 59 degrees Fahrenheit. Adon reported that 2% dehydration adversely affects attention, psychomotor skills, and immediate memory, but not necessarily long-term or working memory and executive functions. Environmental heat can significantly impact exercise performance, as just mentioned, leading to increased fatigue and reduced exercise capacity. There are several mechanisms that contribute to fatigue during exercise in hot conditions. Exercise generates heat, and in a hot environment, the body faces additional thermoregulatory challenges to dissipate the heat and maintain stable core temperature. Blood flow is diverted to the skin for heat dissipation through sweating and heat radiation, which can lead to reduced blood flow to working muscles. This diversion of blood flow can decrease oxygen and nutrient delivery to muscles, contributing to fatigue. Sweating is the body's primary means of cooling down during exercise in the heat. As a result, significant fluid loss can occur, leading to dehydration. Dehydration can reduce blood volume, impair cardiovascular function, and decrease heat tolerance, and increase perceived exertion and fatigue. And sweating also results in the loss of essential electrolytes like sodium, potassium, and magnesium. Electrolyte imbalances can lead to muscle cramps, weakness, and fatigue. Heat stress can affect the central nervous system, leading to central fatigue. The brain's ability to recruit motor units and maintain neural drive to muscles may decrease, reducing exercise performance. In extremely hot and humid conditions, the body's cooling systems may become less effective. If the body cannot adequately cool itself, core temperature can rise, leading to a decline in performance and an increased risk of heat-related illness. And high heat and humidity can increase glycogen utilization, depleting the body's stored energy more rapidly and leading to earlier fatigue during exercise. The discomfort associated with exercising in hot conditions can lead to a higher perceived effort, making exercise feel more challenging and exhausting. The diversion of blood flow to the skin for cooling can reduce blood flow to the working muscles, limiting nutrient and oxygen delivery and impairing muscle performance. And here are the key concepts. Our core temperature is about 98.6 degrees Fahrenheit. 1 degree Celsius equals 1.8 degrees Fahrenheit. The freezing points of Fahrenheit and Celsius, respectively, are 32 degrees and 0 degrees. So you have to convert Celsius to Fahrenheit using a formula depending upon what you're using it for. Humans are heat producers, and their body temperature is regulated by the brain's hypothalamus, which is dependent upon the amount of heat they produce and how much they gain or lose from the environment. High environmental temperatures, high relative humidity, or radiant heat from the sun can impose a severe heat stress on those who exercise under such conditions. So exercise can produce significant amounts of heat, but the body temperature usually can be regulated quite effectively by activation of heat loss mechanisms. Body heat is lost mainly by radiation, conduction, and convection, but evaporation of sweat is the major avenue of heat loss during exercise in the heat. I'm hoping you'll stay cool. This is all that I have for you today. We will be continuing our conversation in chapter 9. I'll talk with you soon. Have a great day.